Greetings, everybody. Welcome to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Sorolla. In today's episode, we're going to take a look at the beginnings, if you will, of electric motors. Now, by no means are we going into all the details. That would be a much more technical presentation or course even. But we want to show off what the basics are, what the guts, if you will, are of the electric motor, which basically boils down to a magnetic field which is surrounding or has immersed within it a loop of current. And the current loop is allowed to spin in a specific way, and that will get us the torque that we need to make the object rotate, therefore electric motor. Motor being a word in this case meaning motion. So we're using electricity to come up with motion, right? Now, to put this on a solid footing, I've gone ahead and thrown some numbers in there. I'm going to make also some comments along the way as we do this to kind of clarify what's happening and why, and also to make clear that this is an example of the kind of thing that makes an electric motor work, but that actual electric motors, of course, are a little more sophisticated for some very specific reasons that we will get to. So let's get started. So let's imagine we have a rectangular loop wire that is going to be carrying an electric current. Now, the current directions are going to be counterclockwise in this example. So what I want you to imagine is the current is flowing in this sort of direction. Now, to make it clear, I'm only drawing the loop itself. I'm not drawing how it's connected to anything else. Because as you might notice, it's a single loop drawn by itself. There shouldn't be any way to make current flow, right? There's no source of voltage, for example, that's present, which means that off in the distance, connected somehow to the loop here, is another series of wires that aren't drawn that will give you your source of voltage. We're also not at this stage worried about whether it is a direct or alternating current circuit. The alternating current circuits are in different videos. We've already done a few direct current circuit videos. So that's one thing to make clear, is that I'm only drawing part of the picture. Also, something I want to point out for my picture is that there is a tab, if you will, here and here, and I've got a dashed line drawn between them. The idea is that this is a rectangular slab, if you will, that's going to be allowed to rotate around that axis. Now, we will specifically show the math that tells us that's what's going to happen, but we're going to constrain the loop in that fashion. So it can't just spin in any direction it wants or any random way. It's got to rotate along this way. So either be spinning, say, clockwise or counterclockwise, if you will. And again, we'll detail that as we go along. All right, so what are some other things that will go along with this picture? Well, we'll have a magnetic field that is going through the loop of current, and that magnetic field will be pointing in this particular direction. So we have that happening like that. Now, also, you may wonder, well, wait a minute, weren't we taught that magnetic field lines come in loops? Yes, they do. And again, I'm only showing part of the magnetic field. The rest of the magnetic field is going off into the distance, if you will, and looping around. We're only showing a piece of it. And there are ways to make this work. So it's not a big deal to have this happen. But just to make it clear, that's what's going on. Last thing to draw in are the dimensions of our loop. It's a rectangular loop. And so this side here, I'll use a little letter A to stand for. So from here to here is little letter A, and that, as you can see, is 5 centimeters or 0.05 meters. And this side, the longer side, will be little letter B, and that will be 10 centimeters. Okay, so we've got that going. You might notice right away that little letter A, at least, is naturally split into two halves, and that will come up too. Okay, so the things we know then are the lengths of the sides. We know the magnetic field, we know the current. What we're after ultimately is the torque acting on the current loop, if you will, at this particular moment. And we'll also mention or talk a little bit about how the current or the torque will be different as the loop itself moves. And that's part of the, complications you run into for an actual electric motor. But let's take a look at this simple case here. And actually, although it might look complicated, this is the simple case for the starting discussion of an electric motor. Okay, so you might recall that torque itself, and I'm going to use the full-blown vector version of it there using vector cross product, torque is equal to a displacement or radial displacement from an axis or a point crossed into force that's exerted. And so one thing that you know from talking about vector products earlier is that in order to get a magnitude out of this, you can't have the vectors of r and f pointing along the same line. They can either be parallel or anti-parallel. And in fact, the amount of torque will maximize if the vector here is at a right angle to this vector. So that's one thing to sort of keep in mind, which is to say, this is what we're after, right? We want to find out what the torque is on our loop of current carrying wire. Well, we need to make sure we maximize things here. So that's one thing we're after. Now, R will be a distance out of either of these. We'll show you which one when we get there. So we already have those numbers basically in play. What we need to figure out is the magnetic force acting on a loop of wire. Now, for a point charge that's moving, the amount of magnetic force that's acting on it, FB, is equal to QV cross B like this, which is, there's the amount of charge on our object, on our point charge. There's the velocity of the point charge, and again, notice it's another cross product, into the magnetic field. So that would be for a point charge. We don't have point charge here, or more carefully, we have lots of point charges, but those point charges are constrained to move along the wire. Now, for simplicity, we've made the wire a rectangular shape, and so the direction of the charges is constrained in such a fashion. But we still don't have an individual charge to talk about, or a velocity for that matter. Instead, we're given a current. So one thing to sort of consider, here's a charge, here's a velocity. The units of charge are coulombs, the units of velocity are meters per second. So if I could come up with something that is coulombs times meters per second, I'd have an equivalent way of speaking about how the charges are moving in a wire, like a current. A current, you might remember, is charge per unit time. So let me write that off to the side, just to, again, remind everybody what this is. Okay, so it looks like that. So coulombs per second. If I were to multiply this by some kind of distance, I'd have my meters times coulombs per second, which would give me the same units as this. And so it turns out, for a line of current, notice the way I'm saying this, it's not a line of charge, but a line of current, the force that you get from magnetism acting on this is not going to be now charge, but going to be current multiplied by some distance. I'll describe that in a moment. Again, crossed into the magnetic field. So, what is this distance? This is the distance, the straight line distance from the axis of rotation. Okay, or some point in space that comes for the current. And again, this is a specific example. We'll adjust it in, as it goes forwards. So, this is what we want. Now, the specific magnitude of this force then is ILB sine theta, right? Just like the magnitude of a torque is equal to RF sine theta. Now again, the theta in either of these equations is the angle between those two vectors. So this theta is the angle between this distance or displacement crossed into the magnetic field. This theta is this distance crossed into the magnetic force in this particular case. So there's some background. So we've got some equations to play with. We have a loop of wire that's carrying current to play with. Let's see what we can do. So first things first, this distance will show that one's easy to get. Let's work on the force first. So what is the magnetic force acting on the wire? Now, again, I've broken this down in this fashion because it's a little bit simpler to conceive of what's happening. But we have really four different segments of the wire, don't we? We have a top segment, a left-hand side, a bottom segment, and a right-hand side segment. So we really have four different pieces of wire to talk about. And we do have directions for a current to play with as well. So let's take a look at these. And so, for example, let's look at the bottom piece of the wire first. Now, in the bottom piece, the current is traveling in this direction. The magnetic field is the same for everybody. Magnetic field is also traveling in this direction. we know that if two vectors are parallel, they're traveling in the same direction, that means that the angle is 0 degrees. Sine of 0 degrees is 0. So sine of 0 degrees equals 0. Therefore, no magnetic force. Now, just to say it, the top will have the same issue. Current will be going in this direction. So let's refer to our picture here. You see the current's going like that. Magnetic field is going this way. Sine of 180 degrees, again, equals 0. Again, no force. Now that's kind of an interesting statement. That means that the top wire and the bottom wire don't contribute to any magnetic force acting on the wire. Now, they're necessary because they're present to carry current, right? If they don't exist, we don't have current in the loop. We don't have a loop. So you have to have those two parts of the wire, but they aren't going to contribute to the forces, right? And that turns out to be fairly important to see. So with that in mind, though, where is the force going to come from? Let's start with the right-hand side first. So let's look at this, and I'll sketch it out this way. So right-hand side, now the current is traveling in this direction with the magnetic field like that. First of all, that's a 90-degree angle, and so that will be equal to 1. And so when we calculate the magnitude, that's an easy task. And in fact, let's do that very quickly. So the magnitude of the force on the right side loop is simply then the current multiplied by the length multiplied by magnetic field. Now, what am I going to put in for L? We've got specific numbers. Which one am I going to use? This is the right-hand side. It's going from here to here. And we said that's the letter B, which is the 0.1 meters. So I can write it like that. And that will be that. And then sine of 90 degrees, sine of theta. Okay, I'll just write that in to be complete so everybody sees where I'm going with it. And let's put in some numbers. So current, I said, was 10 amps. The distance here is 10 centimeters or 0.1 meter. The strength of the magnetic field is half a Tesla. And sine of 90 degrees is 1. You don't even need a calculator for this, right? So we can take a look at this very quickly. 10 times 0.1 is just 1. There's another 1, 0.5. I get 0.5 newtons. All right, so that's the first part there. Let's create some more space here a little bit. Okay, now, what about direction of the force acting on this right-hand side? Okay, well, we introduced in a different video an idea called the right-hand rule for magnetism, right? And so let's do that again. Now, this works the same way because it's in the same order as it did for individual point charges. And so when we did this formula here, we had an interesting way of doing it. Right-hand rule said thumb for direction of velocity, fingers for the direction of the magnetic field, and then the palm for the direction of the force. Or I can use some colored crayons to illustrate those directions as well. So let's do it with my thumb and fingers first and see if we can make sense of it. So the current is going up on the page here like this. The magnetic field is going to the right, so I need to hold my fingers to the right. And when I have both of those together, thumb going up, fingers going right, my palm is pointing down into the paper. So the direction of this will be down. So that is the magnitude and direction of the force acting on our right-hand side wire. Now, if I want to use these to do the same trick, suppose my current is red and my magnetic field is green. So I have this and this. So this crossed into this will give me this direction here. If I can get this to stand up. Let's do that. Very good there, but sir, that's coming out of the board towards you. Now, you might also remember from that previous video, or say things that you learned. Excuse me, I was supposed to be going down, not up. So I had that incorrect. So I have to hold it this way. Make sure I hold it correctly, going down. Okay, so that meant if another way to express it would be to do a little cross like this inside an arrow. So we're looking at the crosshairs of the dart or the arrow pointing into the board. Okay. What about the left-hand side? I'm going to draw it over here. So on the left-hand side, it's the last side we have to talk about. The current is going from here to here, so it's going downwards. So current is going down. Magnetic field is still going to the right. It's also a 90-degree angle, so sine of 90 is 1. And in fact, the magnitude will be exactly the same for the force on the left side as it was for the right. What about the direction, though? So in this case, the current's going down, so my thumb is going this way, my fingers are going to the right, if I'm going to make that happen, and this is fun to make happen in this kind of picture, so down in this way, see if I can make this work. Kind of see my hand there like this. My palm is pointing up towards you. Or, now I've got to do this correctly, the current is downwards, magnetic field to the right, and now, say this correctly, now the force is pointing up out of the paper like that. Same magnitude, so it's the same calculation, but the force on the left then is now 0.50 newtons coming up. Or, if you want to use the symbol that is used quite often, this is looking at the point of an arrow or dart, right? So it's a little target-like symbol. And so we've got those two things. So notice something, by the way, let's reiterate this. There's no force acting on the top or the bottom segment of the wire. That's important. Why is that important? Because if we try to calculate torque, you might be tempted to worry about those two parts of the loop. But torque depends on force. If there's no force, there'll be no torque. So not only do we have no force from either this or this segment of the wire, we'll also get no torque contributed by either of those segments of the wire. So there's nothing to talk about for those. So when we calculate torque on this loop of wire, it's only the right and left-hand side that's going to come into play. All right, let's go on to our next calculation. So, torque, let's remind ourselves, is R cross F in general, and the magnitude of torque is RF sine theta. So if I quickly redraw some of these pictures here, let's just do the left and the right-hand side by themselves for purposes of the torque calculation, like that for the moment, okay? So to remind ourselves, the force that's acting on the right-hand side is going into the paper. So that's the direction of the force here. And the direction of the force on the left-hand wire is coming out of the paper, and we can draw that right here. So left-hand side, right-hand side, and it looks like that. Okay. Now, something else to remind ourselves of, there is a dashed line here about which the wire is constrained to rotate. In other words, that's the axis of rotation. This R is the distance from the axis of rotation. And when you have it set up like this, we've got parallel lines basically. Specifically, the distance needs to be straight, like this, coming from the axis straight to the wire. So either a line that goes like that for the left-hand side, or a line that goes like that for the right-hand side, okay? Now, to go back to our previous picture for a moment, to show off what that's talking about, here's the picture. That distance, the total distance from one end to the other, from the left to the right wire, was the little letter A. Those are 5 centimeters or 0.05 meters. We're only going halfway. So this distance, if you will, is A over 2. And this distance is also A over 2, like that. Okay. So let's do a similar sort of thing that we just did before. Let's calculate the torque acting on either the right or the left-hand side wire. So, torque on the right. So what is torque on the right? Well, instead of R, it's A over 2, like that. The force, now we could write in the number for the force, but I'm going to go ahead and put all the letters in place. And so we saw before that force was IB, capital B, like that. What about the angles? A over 2, in this case, is pointing to the right. This is into the paper. That's a right angle. So it's a right angle. Oh, okay. And that will also give us a right-hand rule question. So we have right hand like this, and the fingers have to be pointing in. So kind of hard to hold my hand like this, but I'll do my best. So probably better to show it off with the crayons. I'll do that in a moment. But thumb to the right, fingers pointing down, and notice my palm is pointing up along the paper. So the direction will be up. Now if I use this in order again, so the red is my first vector, that's the direction of R. The magnetic field is the green crayon going in like that. And when you put those together, the direction of the torque will be like that. Now, one more thing, just to mention this about torque, it may or may not have been a big thing that was talked about when you were first introduced to torque, but let's confirm that here. That doesn't mean the object's going to move along that direction. That's not what that stands for. The direction of a torque vector tells you the axis of rotation, where you're going to rotate about. And more carefully, when you have that going on, if I have an axis of rotation pointing up, for example, like this, that means it's going to rotate this way. So that's the direction. It's going to rotate, in other words, in the direction of the force. That way, to start with, it'll go in and then have a tendency to come back around like this. And so the actual rotation starts in, goes around, comes out, goes back around like this. So you have this kind of rotation happening. Okay. Another way to think of it, equivalent, is that if you were to look down upon the axis of rotation for anything, then if your object is rotating counterclockwise, that's what you're doing. You're looking down on the arrowhead of the vector, of the torque vector. If, on the other hand, you're looking down on the tail of the torque vector, then the rotation will be clockwise. This, by the way, another quick aside, is how we define north and south poles for rotation. If you were to go above the North Pole of the Earth and look down upon the Earth, you would see the Earth rotating counterclockwise. If you were to fly above the South Pole of the Earth from a distance and look down, you see the Earth rotating clockwise. So it's a way to define north and south. That's how we do that. All right, back to our calculations then. So the right-hand torque was equal to A over 2, which is 0.050 meters, right, divided by 2. Again, we have a current of 10 amps. Little b was 0.1 meter, and the magnetic field was 0.5 Teslas. And again, sine of 90 degrees is 1, so I'm not even worried about that. And so for our torque, in this case, we have 0.0125 Newton meters, and the axis is up. So that's the torque acting on the right-hand side. Okay. What about the left-hand side? Let's double check that one, because that's important too. So torque on the left-hand side, first off, it's the same dimensions, right? We're the same distance from the axis of rotation to the wire. So that's A over 2 again. The amount of force was, again, I, little b, capital B. So the number will be the same. It should be an 0.125. There we go. Like that. What about the direction of the torque in this case? Okay, so again, same idea. Direction of the vector pointing from the axis to the wire is to the left. In this case, the force is my fingers coming out. And so if I do that, lo and behold, again, it'll be pointing up. Now, I'm going to have trouble doing this with my hand in this picture for you, so we'll just say that. But we have this vector here for the direction. We have this vector, in this case, for the magnetic field. And when you do this cross into this, oh, lo and behold, the axis is also up. Now, that's important. Okay. Now, notice before, the forces, when we calculated them, they were in different directions. And you might ask, and this is a sensible question, well, if they're equal amounts of force and they're opposite direction, shouldn't they just cancel out? And the answer is, if it was a force question only, then yes, they would. But notice where the forces are being applied. The force is being pushed on the right-hand side down. The force over here, some 5 centimeters away, is coming up. And what that's going to do is give a twist, or as we call it in physics, a torque, right? To twist or to accelerate, rotationally accelerate our loop of current. The total torque then is simply the torque on the right plus the torque on the left. And so 0.0125 plus 0.0125, 0.025 Newton meters, and the direction of the axis of rotation is up, and that's the torque. Okay. Now, final comments before we go. We've done this particular problem. This is for this specific special case, mind you, right? So that to start the discussion, where we have this particular loop of current. All right, we got a loop of current, and its current direction is counterclockwise in my picture, magnetic field pointing that way, so on and so forth, like that. Couple things about this. Let's take a look very carefully at our math, and let me draw this out a little bit differently. So the right-hand torque looked like this. A over 2, little b, I, capital B. I'm going to rearrange it, and you'll see why in a moment. On the left-hand side, also A over 2, little b, I, capital B. But A over 2, everything else is common, right? A over 2 plus A over 2 is just A. So this is equal to A, B, I, capital B, like this. A and B multiplied together is the area of the rectangle, isn't it? That's the area of a rectangle formula, right? Side multiplied by the other side. So we can rewrite this as area times current times capital B, like that, where this now stands for the area. So one of the questions to start this discussion was, show that the shape of the loop doesn't matter. And how would you go about showing something like that? Well, one way to show that is to say that no matter what the loop's dimensions were, ultimately, we end up with the area of the loop. So the area of the loop matters, but not how it's shaped. That's kind of wild. So while we used a rectangle to get there, we could have used any shape. We could use a triangle, we could use a circle, we could use a pentagon, we could use any kind of shape you can imagine. And if we did it very carefully, we would always come up with this particular result. So that's an interesting thing to say. The torque on an individual loop of wire that carries current is this. And of course, this is a loop with current inside a magnetic field. That's where that particular formula comes from. This is then the start of the discussion of an electric motor. So we're going to make this spin. The whole loop is going to spin. Now, here's a problem in practice. This is only when all the angles are 90-degree angles, right? Once it starts spinning, some of those angles are no longer 90 degrees. And in fact, you'll get to a particular point where the angles are 0 degrees and we have no torque. And so what happens? Well, it turns out that in order to make this particular kind of idea work, you need something instead of a DC power supply ultimately. You really need what's called an AC power supply, that is alternating current. And it turns out you need a device called a commutator. Commutator allows you to flip the direction of the current to match the spinning of the loop of wire in order to keep it going in one direction. And so without me being able to draw that on the screen here, I'm not going to try that. Simply say that this particular steps here, what we're showing here, is just the starting point for actually building a working electric motor. But with that being said, these are the basics. In order to have an electric motor, to make a loop move, you need a coil of wire. You need that coil of wire to be carrying current. You need that coil of wire to be set so that it will rotate about an axis. It's constrained to rotate in one direction, rotational direction specifically. And you need all of that to be immersed inside a magnetic field. So these are the things you need to have an electric motor. But with that in play, this is the start of electric motor. All right, everybody. Our support staff is Sidney Gautraw and Sophia Turner. Funding for this project comes from the University of Mississippi and University of Southern Mississippi. We record these videos in Hattiesburg, Mississippi. I am your host, Dr. Christopher Sorolla. As always, thanking you for your attention, and clear skies, everybody.